Okay, guys, are we ready? Yes, there is no time for any homework. It's only time for tests, right? We have to hurry up. There is only test upon a test upon a test. You just have test for breakfast, for lunch, for dinner, and as your SQL. So let's consider continuous random variables, guys. And to understand how they appear, let's consider the situation first. So imagine that you are watching how a barber is cutting hair, and you have made detailed videos of 100 individual hair strands being cut, right? And here, and let's say for simplicity, each hair strand either normalized to its size or they're all the same length, okay? So the hair strand is from 0 to L, and you see here is how you witness the cut, okay? So we can begin to see how are the cuts distributed by imagining that the places where the hair could be cut is discrete, okay? So imagine that we have first of the hair strands that you observed, 1/4 appear to have been cut in the middle or below, and 3/4 appear to have been cut in the middle or above. You understand? So here you discretize the hair. You don't pay attention to where exactly the cut occurred. So if a cut occurs anywhere in here between 0 and 1/2, you say it happened between 0 and 1/2. You just have this bar, right? And if it happened between 1/2 and 1, you can just imagine it happened at 1 if you prefer it. However you like it, right? It happened somewhere here. You cannot tell. Those are big pixels, okay? And if that's the case, I see that exactly 1/4 are here, 1/2 are here. Sorry, what is it? Yes, exactly 1/4 are here, and 3/4 are here. And I want to represent it in such a way that area captures the probability. Area is the probability. You understand? I make it area the probability. That's why the height is 1/2. Look at it. 1/2 multiplied by 1/2, the area of this box is 1/4. Whereas 1/2 multiplied by 3/2 is 3/4. So I scale the height. Notice the height is more than 1. The height is more than 1, so that the sum of the areas of those boxes equals to 1. And so that the probability is relatable to area. You will see in a moment why I do so. You understand? So I made only 2 cuts. Now, second procedure. Next, suppose that we observe that approximately 1/16 of the hairs have been cut between the root and 1/4. 3/16 have been cut between 1/4 and 2/4 from the scalp, and 5/16 of the hairs were cut at a point between 2/4 and 3/4 and onwards, right? You have all those numbers, and here I put on this table. Look at it. You see the red dots is my previous estimate, and now I started discerning more places where the hair was cut. I introduced more nodes, and that means my resolution, my ability, my graphic card, right? My ability to notice where precisely the hair was cut is improved. You agree? I'm more discerning, more sensitive. Good. And look what happened here. And then I have those blue bars. I had red bars, and now I have blue bars. You see, it's slightly different shape. Are you with me? Blue bars. And I structure the blue bars in such a way that you see this is 1/4. The width is 1/4 for each of them. The width times the height will give me the probability that a cut was made in this region. So you understand? The probability that the cut is made, let's say between 3/4 and 4/4, it's going to be represented by a bar where the width of the bar is 1/4 and the height of the bar is so that the product will give you the probability that the hair was cut in here, which I estimate experimentally, because I have this information here experimentally how it was. Okay, are you with me so far?
Professor, what does the y-axis represent?
Y-axis represents the I have a bar, right? If I want to represent area, you will see that it's a good idea. If I want to represent probability as area, I'm going to say that I have boxes. You see, if a cut was made anywhere in each interval, the box over that interval represents the area, represents the probability. So I adjust the altitude so that altitude times width gives me the probability. So what's the probability that hair was cut between 2/4 of the distance to the scalp and 3/4 of the distance to the scalp? It will be 1/4 the width. It's 1/4 multiplied by 5/4. So it will be 5/16. See, 1/4 multiplied by 5/4. And notice 5/4 is bigger than 1. Right? The altitude of the bars can be bigger than 1. The sum of the areas, on the other hand, is always equal to 1. Are you with me? Yes? And then look what I'm trying to show you, right? So imagine you continue doing this process and you have a huge data, right? So you continue doing this process and you suddenly realize that those bars, I didn't draw it further, but imagine I drew this green line. Imagine that you realize that those bars are beginning to align under a particular line. Okay, maybe this line is y equals to 2x. You understand? So the bars, they become very thin and they become almost like a line with a point, and then you see a picture of a line. And those multiple thin bars, they generate a picture of the curve. In this case, the curve is y equal to 2x. Okay. So all you did is just you made your observations more sensitive, and so those thick blue bars are actually thin lines. Yes, or they look like thin lines, and then you have the curve. If you think about, guys, what is integration? You've taken calculus. What is integration? You're just adding up areas of rectangles that are very thin, nothing more, right? So I'm trying to tell you why we measure, why do we have this density curve, right? So we are going to have a probability density curve, which is just something that you structure by convergence, by having sensitive observation. In other words, you see very thin rectangles, and those thin rectangles, their silhouettes trace a curve, and that curve will be the density curve. And areas and information about probability can be answered by integrating below the curve. Okay, I'm trying to show you how that idea might come around. You understand? So probability that x is between a and b is then the integral from a to b, because all you do is you add up the areas of the rectangles. What is this saying? What is the sum? Add up the rectangles that are positioned between point A and point B on the interval. Their elevation, each typical rectangle like this, if you measure it at position x, its elevation is 2 times x, and its width is dx. Right? And that would be, because we know 2x, how to integrate it, will be b squared minus a squared, because the antiderivative of 2x is x squared. Good? Are you with me? You understand how I was able to push it through, guys? If you need more explanation, it's very important for you to grasp it. Let me know that you understand. Melissa, do you understand? Chabeli, who else is here? Yes, that's good. If you don't, guys, you just let me know very fast. You see how you imagine it is that you have those bars, and I made them very thick because it's hard to draw them otherwise. But imagine I was observing how the hair was cut very, very precisely with very tiny intervals. So what you would have is many very thin rectangles. By design, I made those rectangles, their area equate to probability. You understand? So by design, the thickness, the height times the width of the rectangle is probability. So then if I observe just the tips of those rectangles, they look like tiny matchboxes like this. Tiny, not matchboxes, sorry, tiny matches, right? Like this, right? Here is one, here is another, here is a third, right? Can you see that? So, but imagine they are very thick, and you can look at the tips of those matches and you can trace a curve, a silhouette. And the area below that curve will represent probability, because what you do when you integrate, you're just counting how many boxes fit in that region that you decide to integrate over. You see that?
Professor, how do we know if we're gonna get a continuous line?
We don't.
Okay.
No, we don't know that, right? How can we know that, right? Maybe there is discontinuity here. That maybe between this region and that there is a sharp difference. But it's called continuous random variable if what you get is a continuous line, right? If you experimentally speaking, you imagine them, the matches are gradually changing. There's no like something like this, right? So let's say here there is a huge jump. So and no matter how many matches you stick between, there is a huge jump. So the idea is that there is a gradual transition from the elevation of the matches, those boxes. Okay. So anyhow, and so for example, what's the probability that x is between 1/4 and 1/2? I just integrate 1/4 to 1/2 of 2x dx, and I will get 1/2 squared minus 1/4 squared, or 3/16. Okay, I integrate. Why? Because I'm just adding up all the thin rectangles between 1/4 and 1/2. The 2x just represents the elevation of those rectangles. Yes, as simple as that. You see, so when you think of it, it's nothing so deeply profound about it. You're just adding up areas of rectangles. Cool. You can see that, right, guys? So when you think integration is scary, no, it's not. Integration is just a fancy way of saying add up areas of rectangles. This is the width of the rectangle. This is the height of the rectangle. Differentiation is also nothing fancy. It's just you're finding a slope of a line segment. You're imagining the curve built up of segments. Good. So when you realize that, then it's easy to think, easy to come up with ideas without any complicated machinery. So here is the definition. That what we're going to say is that if x is between -infinity to infinity, it's said to be a continuous random variable if the function, it's called density function, right? So the silhouette, this skyline of those rectangles, is called density function. Okay, because it only represents altitude. You see, so this line represents altitude. Yes. And I need to multiply by width to make it area. So they call it probability density function. Right? So if that curve is continuous, then we say that x is a continuous random variable, and that density function is supposed to do the following. The probability that x is an element of whatever set b is the integral over b. So the probability that x actually takes a value here, it's just the integral over b of this curve, because it's just adding up the thin rectangles. So the thin rectangles, however they are obtained, will be like this. That's a thin rectangle. Here is another thin rectangle. And all you do, you just add them up. Add all those thin rectangles, which in the limit, they will be very thin. They will look like lines, right? And that will be adding up the area. I hope it's clear, guys. Yeah. And here is the haircut paradox, which is, by the way, naturally, I'm not sure if you are still suffering from this paradox. Has the second wave begun, or has it been already over? I have no idea. In certain places in Europe, you're locked. I know they had a lockdown in Austria, so you're not allowed to leave your house. That's very smart. My God, how smart it is. How fucking smart it is. So here is the haircut paradox. So a barber whose density function is f of x equal to 2x comes to cut your hair. What is the probability that the barber will cut the hair halfway between your scalp and the tip of your hair? What's that probability? Exactly at 1/2, you see? So this normalizes each hair to be between 0 and 1. 0 is at the scalp, 1 is the tip of the hair. What's the probability that the barber will cut the hair exactly in the middle? Please answer my question, giving the density function. All right, guys, it takes you a long time. I wonder why. Should be a second. What's the probability this barber will cut your hair in the middle? Of course, yes. So Shotaro, it would be 0, right? Why would it be 0? Because mathematically speaking, we are integrating from 1/2 to 1/2 to x dx. And there is no thickness whatsoever to this, so we get 0. Are you with me? Integral from 1/2 to 1/2. Do you understand, guys, that you get 0? Now, here is another question. What's the probability that the cut is made 7/8 hair lengths from scalp? 7/8. Yes, Chabeli, same thing, right? No difference, because what does it matter, 1/2 to 1/2 or 7/8 to 7/8? It's going to be 0 again, yes? You understand what I'm saying, guys? The probability that the barber will cut it at 7/8 is 0. The probability the barber will cut it halfway is 0. And now let's ask in general, what's the probability the cut is made at some point B between 0 and 1? Some arbitrary point B between 0 and 1. Oh, interesting. Now, isn't it surprising? Haven't we just discussed it, guys? So what did I just show? The probability of a hair being cut anywhere is 0, because B means anywhere. Take any point, the probability hair is cut at that anywhere point is 0. I want your explanation. So how could that be? Does it mean you will not have your hair cut? Okay, interpret, right? Like getting a package at a specific time. Yes, I did mention that before, precisely, right? So you understand, guys, what's happening here. In other words, this is another example of those miracles, is that a miracle, as I define it, is an event that has 0 probability of happening, and miracles happen all the time. It just, you would not predict which miracle. So there are 2 interpretations to this result. One interpretation is that you will never guess where the hair will be cut. You understand? If you give me any number, that's not going to be. So he's not going to cut it at 1/2. He might cut it at 0.507, whatnot, right? Some other number, maybe close to 1/2, but not precisely at 1/2. It will not. You will not observe that number that you specify. Okay, that's one way to think of it. Or another way to think of it would be, if you, because you can just do it like this. You can see where the hair is cut and say, aha, it was cut here. That place where you observe the hair is being cut, that little miracle, you will not observe it again. You understand? So when you see after the factum, post factum, when you saw where the hair was cut, if you provided, which is another impossibility, that you can measure it precisely, you understand, the precision is very complicated, yeah? Then you will not observe that repetition. You understand? So that's what interpret says. It could happen once, or right, but it will not be happening. You will not observe it again. Okay, it will be a very rare event. Good. And we talked about the limit NB divided by N, right? We will observe that this limit is equal to 0, but but B can actually happen. That's what I'm saying. It might happen, but it will happen very infrequently. In fact, if you actually observe a hair being cut, that place where the hair was cut, if you could simulate it again and again and again, you will never make the same observation twice. Okay. But for instance, the probability that the hair is cut between 1/2 and 1/2 plus 10 to the minus 8 is not 0. That would be, I think, did I forget to square it? It should be this number squared. It should be, so what I wrote here is not entirely correct. I think what it will be is simply 1/2 plus 10 to the power of, well, I mean, I did it approximately. So that's right. That's fine. I approximated it, right? So the integral, because it's very thin, because the integration is very thin, I can say the result is approximately the same as taking the elevation, calculating it at 1/2, and multiplying by the width. So it's like calculating one rectangle at 1/2, which is 2 times 1/2, and multiplying it by the width. So this probability is approximately 10 to the minus 8. You understand? I did not carry the integration. I just said if the integral is very thin, then I might as well imagine like I'm integrating a rectangle. It's essentially not, the altitude is not changing. So it's a rectangle at 1/2, and the height of that rectangle is 2 times 1/2, and the width is 10 to the minus 8. Good. So that's bigger than 0. It's very small. 10 to the minus 8 is very unlikely, but it is not a 0 probability. So I will see perhaps numbers between 1/2 and something slightly different from 1/2. And here is another example, guys, right? So a girl wants to get a haircut. She can go to one of 3 barbers. The barbers cut each individual hair strand in accordance with the following density functions, okay? Here are the density functions, okay? Are you there? So which barber will you be picking? If you're a girl, if you're a boy, well, if you're a German boy, maybe, right? You tell me which of those barbers do you go to? So this is what a barber will randomly do to, instead of displaying the haircut, he is displaying what the barber does to a particular hair strand. You understand? And then very simple question, guys. What would your haircut look like if you go to barber 1, if you go to barber 2, or barber 3? And then which do you prefer?
So, Professor, would barber 1 you get a really short haircut, and barber 3 I can't see the whole graph, but I'm assuming you get a like
Yeah, it's like this.
yeah, it's you get a long haircut, or you still have long hair. Barber 2 it's a gamble.
Well, so what would the haircut look like if you go to barber 2? Okay, barber 1 and barber 3. So
Right?
let's look at the haircuts. Are you ready, guys? Can you imagine the haircuts, how they are going to look like? Yes? So let's see that. Okay, so this is the girl that goes to have her hair. We, of course, censor their face. So here is what will happen to her if she goes to barber 1. He cuts more or less short, right? I mean, it would not be exactly that, but you see, well, right? It is essentially gathered in the middle. Actually, some of those hairs will be sticking out longer. Barber 2 is rather a bad choice because that's what you would look like. Okay, you would have short and long hairs. Some of them will be long, some of them short. So unless you want to look like you were after a fight, you don't go to barber 2. Barber 3 will keep the hair essentially long, just cut a little bit. Good. Here is the next question. Suppose that the probability density function of x is given by this function, by f of x equal to cx squared, where x is between 0 and 2, and outside that interval, it's 0. So in other words, the random variable always takes values between 0 and 2. First question is determine what is this c, what does c equal to. Go ahead, calculate it. You understand the idea? This with the c must be a definite number. What is that number? How are we doing? 2 answers? 3/8. Okay, let's see. Let's quickly see that. So very simply, guys, how do we do that? We need to integrate from minus infinity to infinity. In particular, most of those values don't matter, from 0 to 2, yes? From 0 to 2, and then we're supposed to get 1, because that integral from 0 to 2 is the total number of values that x can take. It has to take a value between 0 and 2. Do you understand? So, so this is asking, when we know that the probability the random variable takes a value between 0 and 2 is equal to 1. So that integral becomes x cubed divided by 3 multiplied by c. So c has to be, we solve this equation, 1 equal to c times 8 over 3. And so c equals to 3 over 8. Are you with me? C equals to 3 over 8. Good? So now next question is calculate the probability that x is between 1 and 2. I think it's too easy, so we'll do it together. Probability that x is between 1 and 2 is now the integral from 1 to 2 of 3 over 8 x squared dx. And when I carry out the integration, it's 7 over 8. Everybody understands? Yes? No questions. You understand why it was 1? For how I calculated c is that I knew the probability must be 1, and then I know the area must equal to 1. Here is a similar problem. Okay, guys? Here is the next example. We have amount of time a computer functions before freezing up is a random variable with probability density function, PDF, equal to f of x, which is 0 if x is negative, and for non-negative x, it's lambda e to the minus x over 100. So I want you to calculate and do it fast. What's the probability between 50 and 150 hours? All right, so let's do it because it's also simple. So first I need to integrate from 0 to infinity to find what is lambda, yes? So I find that the integral of e to the minus x over 100, it's the same as 100 e to the minus x over 100. And then if I plug infinity and 0, I see that I get lambda times 100, which is equal to 1, because this integral must equal to 1. And so lambda is equal to 1 divided by 100. And from there, I can now calculate the probability between 50 and 150 is the integral from 50 to 150. And it's just the number e to the minus 1/2 minus e to the minus 3/2. Just, you know how to integrate exponentials. E to the minus x over 100, it's 100 e to the, well, basically you got this value here, right? So it's not so hard. Good. All right, so here we talk about cumulative distributions of a continuous random variable. If x is a continuous random variable with density f, then the cumulative distribution of x is the integral all the way from -infinity to a, right? It's just that's where cumulative distributions are useful. And do you remember the fundamental theorem of calculus? Do you guys? Yes, so what is this function, right? So the derivative of this function with respect to a will give you little fa. Do you remember that? If not, we can review that easily, right? So to see this, just observe what happens here. So the derivative of capital F at a is by definition limit as h goes to 0, 1 over h, f of a plus h minus f of a. Okay, and f of a plus h minus f of a is just the integral from -infinity to a plus h minus the integral from -infinity to a. And when I simplify just area, from -infinity to a is simplified, is just canceled out from both of the integrals, and I just have limit as h goes to 0, 1 over h, integral from a to a plus h, f of x dx. Are you with me? You see, because I cut away the tails, right? -infinity all the way to a. In both cases, if h is positive, in both cases, I cut away this piece. And so I'm left with integral from a to a plus h of f of x dx, multiplied by 1 over h. Now, think about it. If h is very small and the function is continuous, this is like the area of a box, right? What's that box? That box is the function at a multiplied by the width of the interval. That's what we did it in a previous estimation, multiplied by 1 over h. F of a times h times 1 over h. So when I cancel everything out, it's f of a. Good? Do you understand? My last step is I say that in the limit, because the function is continuous, in this integral, essentially, I'm integrating over a rectangle. When h is very small, it's almost like a rectangle because the function f is barely changing. It's like this, barely changing. So it's like a very thin rectangle. And that's the simplification that we can do. Yes? You follow, guys, what I'm saying, right? So, yeah. So this is what we observe, right? So again, right, this is the curve. This is a to a plus h, and for all x, it's kind of beginning to look like a rectangle. When when h is very small, smaller, you can see that it's more and more like a rectangle. So it's more like the altitude multiplied by the width, which is what I did here. Altitude, fa, multiplied by width, divided by 1 over h gives us f little fa. So that's the fundamental theorem of calculus, which is extremely obvious if you understand this, that all you're truly doing is adding up tiny rectangles. And between one rectangle to the next, there is not much difference. Yeah? All right, I think I will stop recording now because this is a new idea. And although I do actually, I would have kept you another half an hour, but I'm not sure how many of you will. Let me just show you the police, the Russian video. Okay, it's 1 minute or so. Okay. Okay, watch careful. That's Russia. Goodbye.
Wait, why did you show us this video?
Because I talked about expected value. Why?
That's to be expected in Russia?
Yes. So, people here I don't understand what's average, but I'm trying to tell you that average is not to be ignored, right? Let's say you look at me. I'm a wonderful, what you call it, crown of being, right? The pinnacle of existence. But that's not true about, the iceberg of culture. But that's not true about everything and everyone. Okay?
No, nobody would ever go to Russia.
Well, it's okay. Go to Russia. It's entertaining. Okay. All right. Have a good one, guys. Take care. If you have other questions, do you have other questions?
I don't know. Today's lecture made the most sense because calculus.
Yeah. Don't worry. First exam will be graded when I grade it. That's regarding first exam. Worry about second, third, and final, and whether you answered your questions correctly. Somebody asked me about exams, right? I'm going to upload another exam, which will be the next task, and then the final. Okay. Yeah. All right. So.
Yeah. Professor, I'm still confused on when we know to apply this kind of probability, because you said we don't know when it's going to be continuous.